Kushner from the Department of Physics at the University of Toronto in Canada. And I'm very happy today to host today's first event of the 25-26 webinar series for WCRP's Explaining and Predicting Earth System Change Lighthouse activity. We're resuming this series now, and we aim eventually to have bi-monthly webinars, and the schedule will be announced in the weeks and months to come. But for today, it's a very special pleasure for me to introduce our speaker, who is a world leader in the explosion of research that has brought the methods of artificial intelligence and machine learning into climate science. Today's speaker, Pierre Gentine, is the Morris Ewing and J. Lamar Wartzel Professor of Geophysics in the Departments of Earth and Environmental Engineering and Earth and Environmental Sciences at Columbia University. He studies the terrestrial water and carbon cycles and their changes with climate change. He's the recipient of numerous early career awards from the National Science Foundation, from NASA, from the Department of Energy, and he's also received both of the American Geophysical Union's awards in this area, Global Environmental Changes Early Career, and the McIlwain Medal. As well, the American Meteorological Society has recognized him with the Meisinger Award. What he'll be speaking about today relates to his leadership in this amazing and burgeoning field. He is the director of the National Science Foundation Science and Technology Center, or STC, for Learning the Earth with Artificial Intelligence and Physics, which is the acronym LEAP, a great name for an exciting enterprise. So today's talk is entitled Potential Futures of Computational Science and Climate Simulations, Learning from the AI Revolution. And so the way this is going to work is Peter's going to speak for about 45 minutes, and that will leave us 10-15 minutes for questions. And so I'll give Pierre, a warning at about 35 minutes. And for now, I'd just like to ask Pierre to go ahead. And again, please join me in welcoming him.
Thanks a lot. Thanks, Paul, and thanks everyone for having me. I hope you can hear me okay?
Yes, I can.
Okay, so wanted to discuss today mostly some thoughts. I'm going to present some results, but a lot of that are more like a vision as to where we stand and what we believe with a couple of colleagues in terms of what we expect the future to be in terms of climate simulations. I'd like to emphasize and acknowledge some slides that I got from Stefan Hoyer from Google and Jon Hefner from Pastor Labs. And also the funding agency, the European Research Council, Schmidt Sciences, and the National Science Foundation. So maybe to begin with, when we look at current generations of climate models, so-called Earth system models, they still tend to be too uncertain when we look at many different metrics. For instance, if we look at global surface air temperature, which is depicted here, even by 2060, we can see that there are substantial amount of spread. So that's not really dependent on the type of scenarios and the emission pathways, but it's mostly related to physical processes that we are not representing correctly in many of those models. And you can see that there's basically a very large amount of spread we can see across the different models that are participating here in the CMIP6 intercomparison project. And the issue being that the spread is almost as large as the magnitude of the change we are trying to project. So that's problematic, you could say. It's not just a global issue when we start zooming in. So this is an example here over the US in the summer and looking at precipitation and how that's being represented by different climate models. And what you can see is that when we look at the coarse resolution community Earth system model, so the CAM model, the community atmospheric model, which is here in green, you can see that we are basically missing out many of the extremes, especially the most intense rainfall that is actually so important when we want to look at hydrological risk and impact. But on the flip side, when we start looking at high resolution simulations, we can see that it's a lot more hopeful, especially for those high intensity events. We can see that we are a lot closer to the observations, at least for that particular location, for that particular instance, not always the case. But here we can see that there's actually some hope when we look at high resolution simulations. So that's telling us something that's important about physical processes and how they should be represented. I'd like to emphasize that it's not just, we see a lot of things, especially in the weather forecast. We're going to be talking about that, but it's not just the physical side of the climate prediction and projection problem, but it's also the carbon cycling, which is also problematic. Here is an example from an earlier version of the models, but looking at the land and the ocean carbon sink. And basically what you can see is that when you get to the upper side of the plot here, that would actually indicate a major carbon sink. And for the land, the uncertainty across the models are going all the way from a carbon source, all the way up here to a major carbon sink. So we have huge uncertainties that correspond to many, many years of emissions. And that's actually highly problematic. We'd like to actually reduce that. And that, of course, has implications as well to thinking about mitigation and mitigation strategies, but also for the long-term forecast and projections of those Earth system models. So why is that, and why do we have so many issues? A lot of that is due to the fact that we need to represent complex physics, right? So on the left-hand side, for instance, in the atmosphere, at a typical climate model grid size of roughly 100 kilometers, we have to represent clouds, and especially here, deep convection. And that's actually challenging because that's inherently a subgrid smaller than the grid size problem that we need to represent in some sort of empirical way. In the middle, you also have ocean eddies that are actually very important for ocean heat transport and the accumulation of heat in the ocean, and then the difference between transient and equilibrium climate, so that's also problematic. And all the way to the right-hand side, where we're looking at photosynthesis, which we know relatively well at the leaf level, but then it becomes complicated at the tree scale, but even more complicated at the ecosystem scale. So we're really largely in the dark as to how the ecosystem might be functioning. And so when we look at all of those things, I mean, this leads to many errors that basically accumulate and are compounded together. And that leads to a lot of the uncertainties I showed you before, especially at a time scale and time horizon of less than 50 years. Past that, a lot of that is actually due to emission pathways and the concentration pathways. So, but before that, physics actually really dominates a lot of the uncertainties I showed you before. So, what are some of the strategies we can have to improve climate models? So I showed you earlier that sometimes at higher resolution, things get better. And the reason for that is that when we think of a typical climate model, we typically work at a resolution of hundreds of kilometers or so. And so many of the physical processes that are to the left-hand side of that are at finer scale, we actually need to what we call parameterize them in some sort of empirical way. And so we have some empirical equations that we use to represent many processes such as turbulence, gravity waves, or convections. And that leads to a lot of those uncertainties I showed you before. Now, what we can do is we can actually push for more compute and more resolution, so we can start resolving more and more of the processes that we have here on the right-hand side. For instance, when we run global storm resolving models, we can actually resolve a lot more of the deep convection and deep convective clouds I showed you before, hence the improvement in the precipitation that I showed you earlier. And so that's actually helping because we need to rely less and less on parameterization. And you can go all the way down to actually resolving entirely turbulence. But there's always going to be a trade-off between how much compute we have in terms of the domain size we want to cover, the resolution we want to target, and also importantly, the fact that we also need to tweak and tune those parameters. So we need actually a lot of simulations. We also need to have many, many ensemble members because we want to look typically at statistics because we are very interested in extremes related to climate change. So that's always providing some limits to the compute. Another strategy we could have, and I would like to emphasize that they don't need to be in a position, they can actually go in tandem together, would be to potentially use some sort of upscaling where we could actually learn from fine scale simulations and then basically upscale that and leap across scales, hence the name of the center, where we could actually learn from higher resolution simulations and then plug that back into the coarser scale simulations, all the way making our way all the way to the climate models. So hoping that we can get the best of both worlds between the higher resolutions, but also the scale and the magnitude of the simulations we want to run. I'd like to emphasize, and that's actually quite important, is that even at the finer scale, we'll always be facing the fact that there are many processes we don't know. So such as microphysics, so how we actually form cloud and ice, cloud droplets and ice crystals, the biogeochemical cycle I mentioned before over land. And that's going to be problematic in the sense that we don't have really a ground truthing in terms of just simulations alone. And then what we will need to use is we need to use observations as the anchor point. And that can be coming from like point experiments, in situ or remote sensing. So there's a vast diversity of them. And we will need to use them to learn or improve the representation of those processes, whether using machine learning or using some empirical equations. So that's going to be still critical, at least for a long time being. So these days we are lucky. We are actually witnessing this data revolution. So first of all, we have a massive amount of data coming from Earth observations. We have plenty of satellite observations scanning the Earth and observing the Earth every single day. We also have, as I mentioned earlier, many high-resolution simulations that can tell us a lot more about many of the critical processes, such as deep convection or ocean eddies as well. So we could actually leverage those things. And of course, I mean, there was some convincing that had to be done a couple of years back, but now it goes without saying that a very efficient way to actually harvest those data sets, and especially when we have what we call different modalities, so different forms of the data or different types of observations, basically artificial intelligence is really well positioned to actually target that and harvest those data sets. So I'm going to show you, just to begin with, I'm going to show you a couple of what I would consider successes of using this type of strategy, and then going into some of the limits and what we can learn potentially from the AI revolution to basically go beyond that. To begin with, I wanted to show the example I had earlier about what we call deep convection, so deep convective clouds that are precipitating, very important for rainfall. And what we did in that case is we used high resolution simulations, such as the one you can see here, like a global storm resolving model. And what we did is what you can see on the bottom is going from a high resolution simulation to a simulation, so a coarse graining applied to that, so that we get from a resolution of a few kilometers to a scale that's similar to a climate model scale. And once we have that, we can formulate that as a very standard supervised learning, like a regression test. We are just trying to mimic the effect of the smaller scale, the subgrid scale that we are not seeing in the coarse scale model. And we just want to see the main impact of that in terms of the coarse resolution impact. So that's basically how we formulated that way back. Now it feels like a dinosaur age, in the age of machine learning. What we had at the time, what we took all of the columns of the atmosphere across the globe. We pulled that together. We had some coarse grain value of temperature, moisture, wind, and the boundary conditions at the bottom. Plug that into a deep neural network, and then we're trying to predict the tendencies of temperature, moisture, and also the fluxes at the top and at the bottom, including precipitation at the bottom. And what we did is we then took this trained neural network and then plugged that back into a host climate model. And what we could see is that if you look at the bottom, this is the result. So on the left-hand side, you have the high resolution simulation, so the super parameterized CAM model. And then here you have the difference between the self-evolving hybrid model, where we plug this deep convection represented by a neural network. We plugged that back into the host climate model. And we looked at the difference compared to these high resolution simulations. And of course, we cannot represent snapshots to snapshots because the model is evolving and is chaotic. But we can look at statistics of them. And what we could see is that the statistics are actually very reflective of the original high resolution model. And that's really in contrast with the standard coarse resolution model, where we can see the standard issues with tropical rainfall and some of the issues and those typical biases we have in the tropics. And that's really got us really excited to say that maybe that model is actually pushing the envelope of what we can do. And we could also see that for many of the equatorial waves, we could actually get very good wave dynamics by even plugging this neural network. So it was more than the mean. We could actually get a lot of the nice variability that we expect to see. So that was very helpful. We also looked as part of that, and again, in those online simulations, we looked back at the statistics of rainfall, which I mentioned earlier. And what we could see is, compared to the standard model that I mentioned before, where we typically tend to have this drizzle problem where the model is underestimating the extremes of rainfall, we could see that the model that was self-evolving with the neural network was doing a much better job on the extremes and didn't really have much of that drizzle issue. So we felt that this was really convincing and really hopeful, so that, again, we're going beyond the mean, but we can potentially capture those extremes that are so important for hydrological impact. And what we could see in parallel is that we could also reduce some long-standing biases that we could see in typical climate models, such as the diurnal cycle of precipitation, which is a long-standing issue, also in many weather forecasts back in the days. where what we could see is that the standard CAM model would have this peak in rainfall in the early afternoon. And what we could see is that the high resolution model didn't actually see that. We had those mesoscale convective systems passing over the US. And we could see that with the neural network, we could really see that dynamics and really this feedback across scales between the subgrid happening within the column from the resolved convection from the deep neural network and the interaction with the large scale. So it seems that there's also more than just replicating. I mean, we can actually learn this interaction as well. So that got us really excited. But in parallel, and I think it's important as an anchor point to start thinking about what was happening, in parallel to that, there's been really a transformative revolution in terms of weather forecasting that most of you must have heard of by now. And the strategy there was very different. I mean, the strategy was to take the entire atmosphere and using typically a reanalysis data set and trying to emulate the entire atmosphere with a machine learning model. And what we could see is that back in the days, so back in early in 2018, Peter Dubin and Peter Bauer started looking at that and the performance compared to state-of-the-art physical model, which is here the IFS from the European Center for Medium Weather Forecast, which gives a scale of 100, was actually much lower than that baseline. But in just a few years, we went from that baseline all the way to actually basically outperforming, at least on many metrics on some benchmark data sets, outperforming those physics-based models. So that's really transformative. And as of this year, actually back in February, that became a part of the operational forecasting system at the ECMWF. So that's really transformative, going from pure prototyping in 2018 all the way to operational scale within just a few years. So that's really a transformation and a revolution. I'd like to emphasize, and we're going to get back to this, is that a lot of that was triggered by the fact that there was a very clean benchmark data set, weather bench, from a colleague Stefan Rasp at DeepMind, that really triggered a lot of that revolution because it nicely organized the data so that the machine learning community could actually play and try to assess and develop better algorithms to actually beat this kind of benchmark. And that's basically how it looks like. So this is an example here from DeepMind, from GraphCast here. And you can see on the left-hand side, the observational product, the truth from reanalysis, which is actually a merging between models and data, but the best estimate of the truth. And you can see basically the model on the right-hand side, which is a pure machine learning algorithm, which is based on graphs. And you can see that there's quite a bit of scale when we want to look at that. There's one thing I want you to pay attention to is that over time, at least for that particular model, the forecast is becoming fuzzy over time. So it's skillful in terms of many of the metrics that are mentioned, for instance, especially in that benchmark. But over time, especially this deterministic forecast tends to become fuzzy, and we're going to get back to this. So when we think back about the climate enterprise, I would say, of using machine learning and AI for climate, there's been some success, to be frank, but I think there's still some remaining challenges, on the way. The first one is climate is a really tough problem, right? We have many generalization issues and a lot of counterfactuals that we want to tackle. So it's, in my opinion, a lot more challenging than weather. The success in weather is fantastic, but there are many specific challenges to climate that are still a hard nut to crack at this stage. There's also the fact that we need to look at very, very long timescales, and we tend to have, and the weather models, many of them also have the same issue, is that over time we have a buildup of errors, and that tends to lead to instability over time, especially when we want to have rollouts on centennial timescales. And small errors actually have a huge impact, because we are looking at very small numbers, when we are looking at climate change. There are also some other issues such as physical invariances. So that's actually problematic, because typically we want to conserve mass or energy. Energy is really critical for climate change. So that's actually problematic. But maybe more pragmatically, I mean, the main roadblock has really been just a technical one. The fact that we have typically Fortran-based climate models, and then we tend to have Python-based machine learning algorithms. And it's been very difficult to actually basically plug the two together and to do what we call online learning. So potentially using and learning directly from the observations using those models. So there's been some developments on all of those fronts. So for instance, along with colleagues, many people have been developing bridges, such as ftorch, so we can use and import Python code, such as from PyTorch into Fortran or C++. But still, a lot of that is clunky to a large extent, and we don't have the flexibility that we typically have in machine learning algorithms. And also, typically, we have issues with this online learning because we have this Fortran-based code and we have this Python-based codes. There's been also some improvements. So for instance, to improve generalization. So that's a paper we had a couple of years back, actually, with a colleague, where we can improve that generalization. But still, at the end of the day, those are like long-standing issues that we need to solve at scale so that we could actually get to the final answer. So the question is really, where do we go from there and how do we accelerate progress? So there's been some success, but how can we capitalize on them? But also learn from a lot of what we are witnessing in terms of the AI revolution out there. And I'd like to step back and think about 5 pillars that I'm going to walk you through that are really, in my opinion, some of the drivers and some of the pillars of the AI revolution. And the question is, how can we actually use them and import them and import some of that knowledge and some of that strategy for for climate modeling, but I would say in general, more generally into the physical sciences. So we are discussing a lot with other people like in fluid dynamics, astrophysics. So those are very, very generic problems, and many people are thinking along the same lines. The first pillar, I would say, of the AI revolution is really the fact that now we have very modern algorithm. I'm giving that class in terms of machine learning applied to environmental sciences. And it's amazing to see how the algorithms now have evolved and have become so simple to use so that it really can unleash a lot of new science and a lot of new creativity. And a lot of that is due to the fact that now we have very modern algorithms, and a lot of that is based on 2 key ingredients. The first one is what we call backpropagation, and then the other one is the parallelization at scale of those algorithms. Backpropagation is actually very simple. It's the fact that we typically tend to have a loss, which is here on the right-hand side, and we try to optimize some weights of some neural networks to actually best optimize this loss. And we need to do that at scales because we have millions or billions of parameters. And basically, as simple as that, we just use Chain's rule, right? We just backpropagate the gradients. And if we can estimate those gradients very efficiently, we can actually very efficiently optimize this loss. And that's typically what's done in and what's the backbone of many of those machine learning libraries, such as PyTorch or JAX, where they use so-called automatic differentiation, and we can actually get those gradients pretty much for free and at numerical precision. So that's a huge transformative advance in terms of computing those gradients and then very easily computing and going down gradient to optimize these loss. The second key ingredient is the fact that we can parallelize codes at scale. So the idea of like small batches, so we can actually dispatch them very efficiently. And for transformers, such as the ones that are based on used for large language models, the attention mechanism, which really allows some very efficient parallelization at scale, instead of what we had in the past, for instance, LSTM, so those recurrent neural networks that were storing the information as a big sequence. And that was really annoying because you had to store all of that at once. So now we can actually parallelize that much more efficiently. And that's great because now we can use much more efficiently the hardware that we have. And we are going to get back to this. The second key ingredient, and that happened to be that many of those things actually and those pillars happen at the same time, is just a massive amount of data. And it goes without saying that the more data we have and the higher the quality of the data, the better the models, right? So we've seen that in computer vision, but that's also why people are after like any type of data they can get, not just information over the internet, but any type of videos or even like potentially synthetic data as well. So that's more data basically leads typically to better model. The third piece, and it really goes back to the parallelization, is the fact that we also need to use modern compute, right? So many of the climate models for now, except for a few exceptions, are typically written on CPUs. But most of the acceleration now in terms of the compute is actually done on GPUs. So, and that can lead to massively parallelized computing. Explains also why the stocks of NVIDIA keep going up. I have a friend who got hired by NVIDIA and is pretty happy about that. And the main point being that really they go along very well. So the fact that we can basically parallelize the AI models and the AI training really well, and the parallelization based on those GPUs, I mean, they really go in tandem along with a massive amount of data. So now we can actually use those 3 anchor points as a way to improve the models. The fourth thing, and I think those last 2 bullets, I would say, are a little bit more bespoke in the sense that, but a key component is also benchmarking, right? And the fact that it brings the community together towards a very clear principle where we have very clear metrics of success. We have some of that for climate models, but it's typically more of an intercomparison, like the CMIP exercise I showed you before. And we have less, even if colleagues are actually working quite a bit on that, but we are less clear sometimes about the benchmarking that we have. And for weather bench, for instance, for the weather forecasting, that really drove a lot of the community forward, in the sense that a lot of people knew exactly what they needed to get and how to actually improve the algorithms to then improve those metrics. So that was really transformative in that sense. So benchmark data sets shouldn't be underestimated. They really drive the community forward and are really critical for that. And finally, for me, that's potentially the less appreciated, but potentially one of the most impactful things, in the AI revolution and some of the new machine learning libraries that we have, is that really disconnects a lot of the domain science and the conception from the optimization, right? The fact that we can focus on the science, it can be very agile to different hardware. We can run on CPUs, on GPUs. And it's a lot more inclusive in the sense that junior scientists in particular can very easily get into the code. And this is just an example here where in class, we know we developed this spatial and temporal structure, so a convolutional neural network and an LSTM to investigate some climate structure. But the main point being that in just very few lines of codes, we are doing things that are relatively sophisticated from a AI perspective. I mean, this is not state of the art, but just to give a sense that we just need very few lines of codes, because a lot of that is actually disconnected and a lot of that is done under the hood for us. So that's been really transformative to drive the community forward and to really accelerate progress in that community. So that's really important, I think. So based on that, I like or the vision we have and we share with a few colleagues is how can we actually bring the climate modeling community to kind of the same type of acceleration we've seen coming from, especially from the AI revolution. The first thing that we need, based on the pillars I mentioned before, is we need to have modern code and compute, right? We need to be able to typically have more inclusive type of codes, higher level type of codes, typically Python-based, because students now mostly know Python. They might not want to learn yet another language. And typically, you would want to also leverage many of the new computing infrastructures and hardware, and in particular GPUs. So this is an example here where we use the JAX machine learning libraries, and those are colleagues here demonstrating the impact of using JAX for an ocean model. And I'm going to show you that in a minute. But basically, what they could show is that by rewriting the code from Fortran to JAX, basically over the summer, so that's the work of John Hefner now at Pasteur Labs, he could show that he could get pretty much to the same performance on MPI, which is this multi-CPU infrastructure, even though JAX is really not optimized for that. But in just one line of code, he could also leverage GPUs, which he had never been able to do when he only had the Fortran code. He would have to really, it would have required an entire rewrite of the code. So that's really transformative in terms of the agility it gives to tap into different hardwares, so that's very, very important. The second thing is that it becomes pretty obvious, but once we're in that space, and especially if we can tap into what we call the differentiability and the fact that we can automatically differentiate through the code, then it becomes pretty seamless whether we're using AI or physics. So we have quite a few experiments now in our group showing that whether you're dealing with physics-based parameters or you're using weights of a neural network or even initial conditions potentially of a simulation, you can really treat all of them as the same thing, as some parameter that you need to optimize based on some data. And that really provides, I think, a backbone to unify physics and AI. And we can see that really happening now across all of the different fields of physics and physical sciences, again, from astrophysics and cosmology to all the way to the neurosciences and fluid dynamics. So this is not just in climate. We see that happening right now across fields. And finally, and maybe that's one of the key thing and unique aspects of climate is that once we are in that space, we don't need to just rely on simulation data. We can actually tap into a lot of the observations that we have. And finally, we can get climate models to use much more efficiently a lot of the observational data that we have. For now, we are only using just a very tiny fraction of that because it's very difficult to tweak and tune those models. But we can really accelerate that a lot once we have this new platform and we can actually do that. And the reason for that is why do we want to get back to data is that even the high resolution models are still imperfect, right? So we still need to get back to data at the end of the day. That's the ground truth thing. And finally, a key component of that is also to start thinking about having the data infrastructure that supports that, especially as a community, right? How do we bring that together? How do we build the data infrastructure so we can work together in an open, transparent, and typically reproducible way with very clear benchmarks of success so we can really accelerate progress together? The same way I mentioned for Weather Bench, we've been able to do that for weather forecast. So I'd like to maybe step back for a moment. So those are not just results from our group, but what I consider exciting results from across the board and colleagues across, and where I see some successful examples of such strategy across different fields, especially related to the Earth system for that particular case. The first one, and I would really consider that a breakthrough at the time, was to, and it got a little bit under the hood, but under the radar, but I think it's actually very important, is that code refactorization of the Veros Ocean model I mentioned before. So they moved again the code from Fortran to Python Jax, so a code that's a lot easier to use, basically over the summer, and they could seamlessly basically leverage multi GPUs and run the model at a resolution that they had never been able to achieve before, so at 0.1 degree resolution here, and simulated on 16 NVIDIA A100 GPUs. So that was really transformative in the way you could actually do that. And as Jon Hefner, who actually provided this slide, framed that, is that this modern high performance computing in Python and in JAX is simple to write, right? Because it's Python based. It scales really nicely because we can leverage a lot of the tools, especially in JAX for that. And it can also run on many different hardware just by one line of code, right? I mean, the only thing you really need to do here is to change the type of platform from going from one CPU to multiple CPU or to GPU right there. So that's really transformative in terms of this agility and flexibility of those models to different type of hardware, but also the feasibility and the flexibility and ease with which we can use those models. So I think for me, that's really transformative. The second example, which is more on the fact that and the differentiability and how we can fuse data and simulation data, is coming from Google. And last year, they released this so-called Neural GCM. And it's actually very similar to what I showed you before in the sense that what they have is they have a physics-based, what we call dynamical core, so the advection and how you move the fluid around, coupled to a neural network, which is representing all of the physics in each individual grid. So radiation, convection, turbulence, and gravity waves, and so on and so forth. And the key technological breakthrough here was to actually make that dynamical core differentiable in the sense that we can pass on the gradients across that, which is kind of the bottleneck I mentioned before, this clumpiness and the fact that it's challenging to do that now. And once you have that, what you can do is you can basically roll out over multiple time steps and you can optimize over relatively long timescales, so a couple of days in that case. You can actually train the model so that there's some consistency, and that avoids a lot of the blow up and the stability issues I mentioned before. And that really leads to this long-term consistency of the model. So that was, and that can be trained end to end now by using some observational products, some reanalysis product right there. And when they did that, what we could see is that, first of all, it leads to this non-blurry forecast. And now we can get the crisp details that we had before over, this is an example for total column water vapor. But they could also show in other work that they could also fuse with different types of observational data. And so that's really transformative in the sense that it really shows how we can bridge between physics and also machine learning as a way to fuse that once we have this kind of differentiable framing. And again, in that case, leveraging a machine learning library here, JAX. The second example I wanted to very quickly mention is some work we've been doing actually with a great student, Jianing Feng, where we've been trying to use that for this type of strategy for land. And land modeling has been historically very complicated because we typically don't know the underlying equations. We have some idea, but they tend to be very complicated. And oftentimes we have parameters that are very varying across the landscape, right? So unlike in the atmosphere where the physical laws remain the same across, for the land, the type of species that you have, the type, of land cover can dramatically influence, the land carbon cycling and the land water cycling as well. And so what we did is we actually reframed a relatively simple carbon pool model, and we actually redeveloped that, and refactorized that into JAX. It can run on any type of infrastructure, on laptop, on high-performance computers. It can be run on CPUs or GPUs, or even potentially on the cloud. And what we did try to do is going a little bit beyond what I just showed you before for NeuralGCR, but also plugging directly some sort of linkage to observations, and in that case, to satellite data. So we have what we call an observation operator. And the advantage of that is now we don't need to directly have access to the truth and to the state, but we can directly use the observations to infer what the state of the system should look like. So, and because in that case, the observations, there's an operator in between, and that operator happens to be differentiable, so we can take the gradients across. And so now, just based on the observations, which are sparse in space and time, we can actually propagate that through the system, and the system keeps some physical consistency so that we can actually propagate that long term. So we try to bring again some sort of hybrid perspective between long-term consistency due to physics, and then some of the details we don't know that are constrained in that case by machine learning, and directly by the observations, because we don't have a ground truthing in that particular case. We showed the power of this method to assess a couple of things. The first one was to try and retrieve one of the key parameters that regulate the land carbon cycling, which is how photosynthesis is being reduced as a function of soil moisture or soil water content. We know that when the soil gets dry, photosynthesis is being reduced, but we typically don't know the exact shape of the function and how that's being reduced across space. And what we could show is that by just ingesting data over time in a sparse fashion, we could actually retrieve this function through the consistency of the model over time, which is preserving the carbon and the water pools. And we could actually just, as you could think about that, it's some sort of assimilation, but so that we can directly retrieve some unknown function, which is actually here replaced by a neural network. So it doesn't matter whether we are using physics or we're using machine learning. At the end of the day, it's just a bunch of parameters that we are trying to optimize for. So we can just learn new functional relationship. That's the main take-home message. The other thing we try to do is that not just trying to learn functional relationship, but trying to see how the landscape is actually organized. So we know for a fact that plants tend to adapt to different environments, but it tends to be very challenging to represent that in mechanistic models, right? Because we tend to have only one viewpoint of the world, which is what we call plant functional types. So we just slice the world in different types, but it's very difficult to adapt the parameters of those species or of those plants to the local parameters, and it's very difficult to actually know that altogether. So what we've done is we've used.
Just wanted to let you know you have it's 38 minutes after the hour, and you should wrap up next 10 minutes or so or less. Thank you.
Yeah, perfect. So in that case, we are using the same mechanistic model here, and we have the observations, and we are just assimilating those observations to constrain the unknown parameters that are varying across space. But so we take those observations here, we assimilate that, we want to constrain the parameters here. But what we didn't want to do is just constrain every single parameter pixel-wise, because that we have very few observations. We have monthly satellite data, some in situ observations, but that would lead to a very poorly constrained system and a lot of variability across the parameters. So that would be very ill-posed in a sense. And instead, what we said is that we know that the parameters or traits of those plant types should be dependent on climate, on plant functional type, on soil type, and age. And we just said, let's learn that. Let's learn basically how plants adapt, right, to a particular climate. And because we don't know the functional relationship, we can just plug a big neural network that would actually bypass that and try to learn that all together by assimilating the observations and then optimizing that spatialization network as a function of climate, plant functional type, etc. And then We optimize that again using backpropagation, as I mentioned before, and then we can actually use that model to predict, right? And we can do different things. So at the top, you can predict over time, for instance, the land carbon sink across different regions of the globe. So we are very interested in that. But we can also look into the parameters and what they learned. So, what was this spatial structure that we learned and how are parameters varying across space and time? And basically how plants did, why plants did adapt at a particular location. We can also bring some explainable AI strategy to actually look into those parameters and see how they are varying over space and how key parameters are actually changing that. And just to convince you that the model actually works very well, so it's actually, we are being very careful here in terms of training and validation, so that are completely held out regions of the globe. And you can see that across many different variables that we are trying to predict. So leaf area index, the amount of photosynthesis here, carbon uptake, or the amount of biomass here. We are basically doing a very good job, even at pixels that were not being used as part of the training. So there's no sign of overfitting, and we have this kind of extrapolation capacity. So we learned something pretty fundamental about the landscape and how plants are actually adapting globally, you could say. And once we are in that space, again, we can actually start looking into what was being learned in terms of the parameters, and we can learn potentially new things. So there are things we know, for instance, photosynthesis, and the efficiency of photosynthesis is parabolically dependent on temperature. There's an optimal in terms of temperature for photosynthesis. This is quite well known, but we never impose that. We directly retrieve that just from the feeding of the network itself. But we can also start thinking about new things. So for instance, if we look at the amount of respiration, so the release of carbon from a forest, we know that it should be dependent on tree age and on forest age, right? As a forest grows older, it tends to become more and more bulky, if you will, and tends to release more carbon, right? We have like a higher breast height, so we tend to have like larger diameter of the trees, if you will, and so what we can see is that in that particular case, we can see that the respiration is actually changing dramatically as a function of tree age. And that's something that's been really challenging to show, but we can just basically learn that automatically from the data. The last thing it's telling us is also like what are the parameters of the model we can identify based on the data that we have from satellite, and what are the ones we cannot constrain. So we can actually do some perturbation analysis like Monte Carlo, and we can see what are the parameters we cannot constrain. And that can be very informative because then we can actually target that potentially using some new missions, could be satellite missions or in situ observations, to try and refine those observations. So really it's a back and forth between the simulations and the data. We can eventually keep on improving the simulation and the retrieval. So just to wrap up very quickly, I just wanted to emphasize that. So this is a vision we had in the paper last year, led by my colleague Veronica Eyring, and really emphasizing how machine learning can really swallow that and go across scales, right? We can actually learn from high resolution simulations and fuse that potentially with data, and also potentially generate a lot of more ensemble members, but also do a lot of the downscaling that we want. But what we need kind of the type of infrastructure I showed you before, so we can start thinking interchangeably between machine learning and physics altogether. And that's kind of my view of the world right now, is how can we actually build kind of this Legoland where models, we shouldn't think about like AI models or physics-based models, but based on the task at hand and what we want to actually do, we could actually replace those things. So sometimes you just want to replace one piece of the Lego, but sometimes you want to replace the entire atmosphere. So for instance, you want to look at weather forecasting. Maybe in that case, you might not need a lot of the physics, right? You can just use a pure AI emulation because it's going to be very efficient. But sometimes you want to get more into the physics, or you want to look at counterfactual. So you need to have the capacity to actually communicate. And as a colleague put it, you need to have the bricks that can actually connect to each other. And that's really where this kind of new type of infrastructure and differentiability is going to be very critical for that. So with that, I'll be very happy to take any questions, and thanks for your attention.
Thanks very much, Pierre. That's a wonderful seminar and a great tour of some stuff that, like you said, it was the the early period. It was only 6 years ago or so that all this started, and it's just remarkable how quickly things have advanced. I want to ask. I'll indulge myself in asking a first question, and that's in the perspective of this particular series, which is the explaining and predicting Earth system change Lighthouse activity. Its interest is in annual to decadal climate variability, explaining and predicting using decadal forecasting to of course make predictions, but also to interpret recent changes in climate. And I'm wondering, the project is built on like our idea of workhorse GCMs. We have these standard GCMs. We use them for all sorts of purposes. We get a lot of experience with them. And it gets a bit to your last point. I'm wondering if you could just comment on how that might change, like how our practice is going to change when it comes to, swapping customizing these tools much more specific to each purpose, and if that's going to be revolutionary or more evolutionary. So I hope you understand the question. It's kind of a general one, but just I'd love to hear your comments.
So if I just to maybe reframing that, you're asking about sources of predictability and explainability to some extent, right? So
yeah, that's right.
Where I see a lot of potential is again those gradients, that you can get. So you can really start thinking and poking a lot of that. So I showed a couple of examples, such as for the land, we are using a lot of that to start really querying and investigating what are the sources of predictability and how we can use that across. And you could think about that. We are doing some of that also for sub-seasonal to seasonal timescales or weather timescales. So that's, I think, is very useful for that. Of course, what you need to have is you need to have trust in your model, right? Especially the AI model. Are they just replicating the past, or do they have like real, like physical insights? So there are some cool experiments, such as colleagues in Oxford that have been rotating the Earth, and then you can see that they don't work so well eventually. So some of the physics might not be kept. So I think that's quite interesting. There's like another piece I didn't really mention, but I'm going to see you next week, so I'm going to show that there. Talking about how we can use AI also to compress information, right? So this idea of like latent embedding and latent space, and I think that's very powerful in the sense that it can really teach us a lot of things about the climate system and about like physical processes that have been historically challenging. Like thinking, for instance, we are looking a lot at deep convection, the aggregation, like how that can be clustered, the life cycle of that, what is controlling that, how do you actually transition from being unorganized to organized, or like the example I gave from, adaptation of plants, So I think, and it's funny because there was a talk actually at Columbia a few weeks ago where someone from astrophysics was saying it's been transformative in terms of the predictive power, AI, but what have we learned? And he had a blank slide, and he said, we've not learned. I mean, that's what we've learned. I think that's a bit extreme, but I think there's a lot to be done yet in terms of the understanding and going back to physical understanding, new things, especially when the data is so challenging. Like when we look, for instance, at those global storm resolving models, they are really challenging to interpret. But now we have like cool tools, like to start thinking about, like what are the regimes, like what is critical for transition and things like that. So I really see that across the entire pipeline.
Okay, thank you. That's a great great for some future discussions to have. Okay, I'm looking at the questions that are coming online, and I will go more or less in order. Actually, Zhuo Wang has two questions, and I'm going to take the less specialized of the two. And the question is, generally, how do you see AI models addressing the issues of generalization and out of distribution performance? And the earlier question from Zhuo was about how SPCam, the comparison with SPCam seems to show the NNCam kind of having greater variance for more intense precipitation events or greater frequency. So there's a bit of a question about what's going on with these models.
Yeah. On the first question, I mean, I think that was my point, that this is the ultimate challenge, for climate. I mean, ideally, we were chatting with Chris Bretterton last week, ideally you would want to use just historical data and project the future, but that's been very challenging because you have a lot of things happening, like different, what you could call counterfactual. So you would want those models to be doing the right thing in terms of generalization, but also capacity to be causal to a large extent. And for now, we can see that many of those models are not. They just use correlations because that makes things pretty easy. So that's a huge challenge. But I would say that's true for climate. And that makes it really interesting in a sense. But that's true across the board. Like, how do we generalize, even when we think about AI and large language models? Like, can they be fully creative, right? Are we just beyond the envelope, or are we interpolating but smartly in between? So I think those are very open questions about out of distribution prediction. And on the second one for the variance, I'm not sure I got the question right, but
I didn't describe it well. So in your slide 9, the right tail of NNCAM extends above that of SPCAM. Does it mean that NNCAM predicts extreme precipitation values out of the distribution of SPCAM? And if so,
I wouldn't look. Thanks. I wouldn't look too much into that. In fact, we've been very careful after that, and we had a paper in PNAS a couple of years back now, where what we showed is that if you fine tune and you're being very careful, in fact, you still underestimate the most extreme events. If you go way down, it was cut, it was not intentional at the time. We just cut there where that was. But then we looked a lot lower. And then if you look at the most extreme events, what you see is that you underestimate them. And what we could show is that a lot of that is due to the fact that you don't have access to all of the information that we need. And that was part of this interpretation piece. What we showed is that what you need to have additional information, which is about the clustering. And that's something you don't have. So the organization of compaction, that's something you don't have just from the core scale. So I think it's telling us a lot of things about the fact that, sometimes just using the core scale to estimate everything about the fine scale is insufficient. You might need additional information. And that could be critical, such as for precipitation, but you could also think about radiation, like top of the atmosphere radiation is also very dependent on the clustering. So potentially you could actually extend that thinking and say, it could actually be important. We don't have that at coarse resolution. So that could be a bottleneck.
Right. Yeah. Interesting. Yeah. There's a question on data biases and gaps from Lucien Jordan Chouassi. How are the biases that are caused by data gaps corrected? For example, a case in Africa which does not have a dense data collection network for the case of rainfall.
Great question. That's a major issue, right? At the end of the day, and great question about, especially we've been looking a lot at West Africa and then predictions. That's a huge problem. Like, if we cannot benchmark, if we cannot really validate, we are always going to be in the dark, and hence the importance of continuing and trying to remove potential biases. We have quite good, observational data, in the global north. We really need to push for global south, especially precipitation is a key thing. We have algorithms, but we don't even know how they perform because the envelope is so large, right? So that's a huge problem.
Yeah, that speaks to a need to prioritize resources around those data gaps.
Right.
Especially these days. Yeah. Here I have one question from Doug Smith. Thanks for a very nice talk. Do you think AI climate projections will have to be trained on climate models and so will inherit their errors, or is there an alternative?
Good question. I think that's the holy grail. For now, it seems that, the strategy that people have had was to use climate models, but my feeling is we keep getting surprised with AI. It started very localized, and then it's eating more and more of things. So frankly, I don't. I think we need to keep an open mindset. Yeah, but we are seeing more and more applications. Like the schematic I had at the end. It goes from downscaling to ensemble generation. I didn't have time to talk about that, but looking at extremes, that's a great tool for that. We can start fusing different types of data. So it's just coming across as a very versatile and very powerful tool to do many different things. But for climate, again, and that's kind of that question that's related to the first question. At the end of the day, the generalization, the counterfactuals, the causal representation, those are really, really critical issues, that we need to, and it's easy to replicate. For instance, there's this climate bench data sets from my colleague Duncan Watson-Paris, it's very easy to replicate with a very simple neural net. Now, if you drop CO2 right away, you will see that the model doesn't work at all. So I think that's problematic, right? It's easy to correlate. It's much more difficult to create causal representation.
Yeah, and you're speaking to the some of the perils of benchmarking and how we have to be so careful in
Yes.
achieving those benchmarks, that they're very important and necessary, but at the same time have limitations. There's a nice question, maybe a more hopeful question from Arna Litzinger here. Do you think we will be able to actually learn physical laws from machine learning, for example, for microphysics?
That's a great question, and that we are quite hopeful. Yeah, microphysics is a great example. Actually, I have very good colleagues, or we have very good colleagues at LEAP, working on microphysics, and that's a direction that people are taking. So I'm quite hopeful we could actually improve some understanding. That's been shown for cloud cover, like for ocean eddies. My colleague Lausanne recently, Pedro Azanzande, they had a nice paper also looking at closure. So I think we can push the boundaries of that. So that's quite nice. For me, it's not. I tend to see that as it's not just AI, but I see that as a positive feedback loop. We go to AI because it's great to actually harvest data, but then eventually we want to get back to physics, right? That's why we got into that business, or at least myself. But I see that as hopefully a virtuous circle.
Yes, yeah, they're not mutually exclusive, and you learn a lot by going back and forth, and
Exactly.
it provides a motivation for those of us more senior to continue to train people in the basics.
And if I may, there's a lot of I tend to come here, I think, with a lot of humility, right? What is the data teaching us? Mm-hmm. So there are things because sometimes you have some gut feeling, some of that hopefully is true, hopefully the majority of that. But sometimes you get surprised, and that's also pretty cool, I would say.
Yeah. There's a question that popped up in the chat, which I can offer here from Davy Emenake Andrian Siori, and I apologize for the mispronunciation. Do you have more tricks to provide when applying these methodologies at a regional or even a local level?
Yes, there are many tricks. So you can, for instance, very similar to what we are doing for large language models, you can fine-tune the models for a particular localized task. You can refine the resolution of those models to a particular location. Yes, so there are many tricks, like fine-tuning in particular, that you can use at a local scale. The downscaling is an obvious one, right, where we can do. I think that's a great tool. Like AI is a great tool for that, and many people have shown that by now. So yes, for sure.
Great advice. Okay. Well, I'm going to just ask if there are any further questions.
Yes, can I please ask one question?
Yes, go ahead, Maureen. Yes.
Yeah, sure. Thanks so much, Pierre, for your talk. It was very intriguing and very good to hear that there is some development. So my question was on the parameterization, where you shared good example, the parameterization of optimal parameters, and you said that you do that for a long time, and the model learns from the memory. How is the AI able to distinguish between where the model had picked some errors in the model memory and show that this is a peak that was an off peak or out of range, and then distinguish from what is normal in the long run?
So you mean for the climate simulations or for the land simulations?
Land simulations. My question is on the land simulations.
Yeah, so that's a bit tricky. So that's getting a bit into the technical things. But what we are doing is, well, in fact, it's quite cool what we do, I think. But what we can do is we use sparse observations, and we can back propagate them. So we have observations. So we don't directly observe the Earth. We don't have directly the state, but we know that there's an observational operator in between. So that's representing the sensor and how it should work. We back propagate through that to get into the state. And then there's a lot of physical consistency, like mass balance, energy conservation, etc. And then we propagate things through that over multiple time steps. So even if you have indirect observations that are sparse in space and time, they eventually constrain the entire dynamics over time through that differentiability, through the gradients. And what we can even do, and in fact, it's actually very important to do that, is to even estimate the initial conditions. So we can estimate the initial pools, which is very useful because typically for land carbon models, what you need to do is you need to do a very, very long spin up. You need to equilibrate what we call your carbon pools or your trees, basically, what size they have when you start the simulations. And that can take hundreds and thousands of years, right? And that's highly problematic. And what we can do is we don't need that because we can just optimize everything going back. And then finally, there's another piece, so it's quite complex, but there's another piece, which is this spatialization network, so that we also bring together, even when we have sparse observations at a given point, they constrain everything also in space through that. So we have the space consistency and the temporal consistency. And one thing that's pretty cool is we can check, for instance, one thing which is really crucial, such as the interannual variability of the land carbon sink. And we can see that the model is really good at capturing that, which tends to be a huge challenge for most models. So it means we really have that good consistency across space and time.
Okay, great.
I hope that
Thank you.
answered.
Yes.
Pierre, the questions are still rolling in, but we've reached the top of the hour, and so with respect to the time, I'm going to have to bring this to a close. I want to thank you again for a wonderful presentation and overview of past and upcoming work, and thank you very much for generating such an exciting session to kick off our new series in EPESC. Thanks very much.
Thanks a lot. Thanks for having me. Have a great day.